Speaker in this session is Katie Thompson from the University of Leeds. She's going to talk to us about a recent field campaign that she was lucky enough to go on.
Yep. Is this on? Can you hear me?
Yeah.
Okay. Yeah, so yeah, I was lucky enough to I was lucky enough to go on a campaign. I literally only just got back last week. And it was a 6-week campaign in the Labrador Sea. And for those of you who don't know, that's the sea that lies between the east coast of Canada and Greenland. And I was looking at ice nucleating particles. That's what INP stands for. In relation to the mixed phase clouds that we see in that region. So just to start with, I'll touch on what ice nucleating particles are and why we care about them. So in a cloud, we see that water droplets tend to stay in liquid form until they get to around about minus 35 degrees C. That's if nothing else is interfering. So clouds can be in this super cool, metastable state, but below zero until about minus 35. However, ice nucleating particles can change that. So this here we've got a cloud, and in this case we've got some ice nucleating particles that are immersed in the cloud droplets. Now this is just one example of a pathway that this can work, but it's the most common in mixed phase clouds. So what we see happens is that the cloud will cool to a temperature where the ice nucleating particle is activated, and then we start to see ice forming. But because we're in this super cool state, the supersaturation with respect to ice is much greater than that of water. So the formation of this ice starts to grow rapidly at the expense of the surrounding liquid water droplets. So then these ice crystals can rapidly grow large enough to initiate precipitation. And this is important because it can affect both the cloud lifetime and its radiative properties. So it has implications for climate because by reducing that cloud, we're getting less reflectivity of incoming radiation. And it also has implications for precipitation in terms of where that's happening and how much we're getting. So the sources and concentrations of these ice nucleating particles in the atmosphere in general is really important, but it is particularly important in places like the Labrador Sea. So the Labrador Sea, as shown in this picture here, we get quite vast amounts of these low-level mixed phase clouds. And it's also within the Arctic Circle. And the Arctic is warming much faster than the rest of the globe in terms of climate change. And so, first of all, we want to understand what's currently going on and what the balance between ice and water droplets and how that's being influenced by different ice nucleating particles currently. But we also want to understand how that might change in the future with changes in like the climate. So there might be changes in the sources and the temperatures in this region, and we need to understand how these ice nucleating particles may be playing a role. But at the moment, we have very little understanding about what these sources are and what concentrations are in this region in particular. So that was what the main aim of this campaign from our point of view was, to try and analyze these concentrations and try and do a better understand the potential sources. So I was on a cruise, as I already said. It was a joint cruise between two campaigns, Sienna and M-phase. M-phase being mixed phase clouds, which is what I was part of. This is a picture of all the scientists on board. And this is just our M-phase group. Mark really is there. He looks like he's been sort of photoshopped in, but he just was wearing a t-shirt. He was actually there though, I swear. Yeah, and this is just I wanted to sort of just show like what it's like being on a cruise. This is one of the fjords in Greenland that we stopped at. This is the ship itself. It was the RRS Discovery, hence the DY151. There's some amazing people that I got to meet. It was genuinely like such an amazing experience. I had a great time and would definitely do it again if I had a chance. But obviously the science is more important right now. We set off from Reykjavik in Iceland on the 21st of May and then headed over to Greenland. this stop was kind of unplanned. It was partly because there was a storm, but we were able to get some really good measurements there. Then we went round, we stopped at Newark in another fjord, and then up near Sissumet, before spending some time at the sea ice edge to get some more pristine background measurements, which was of interest to everyone on board. And then we eventually made our way back down, and this doesn't come to an end, but we did end up coming back to Southampton. This graph, by the way, was produced by Sarah Barr in my team, and I just think it's a really good way of visualizing where we went and where the Labrador Sea is for anyone who doesn't know. So yeah, we got to see a variety of different locations, like be able to look at the more terrestrial stuff from Greenland, because we were particularly interested in potential dust sources or outflows from the rivers in Greenland. And we were also able to sort of look at that background, as I said, from the sea ice edge. So what was I doing in particular? I was particularly interested in the size resolved concentration of ice nucleation. So I had this tiny little cascade impactor with 4 different size stages. There it is there, connected to this simple pump. So because it's quite small and it just needs that quite portable pump, it's quite easy to set up and change and put in places where other bigger instruments couldn't go. But it could only be run at 9 liters per minute, which is quite a slow rate, and because concentrations of aerosols in general in that region are quite low. I had sampling periods between 20 and 72 hours in order to get like a decent enough signal to be able to see anything. But yeah, as I said, because it's nice and small and portable, I was able to put it up on this little mast up here, right at the front, away from everything else, away from like the shipping emissions. And I also had a tiny little OPC running alongside it to be able to analyze what the aerosol concentrations were whilst I was taking my measurements. So then I had to analyze that. So each of the impactors had filters on, which I then washed into suspension. That suspension could then be pipetted into tiny little droplets on this cold stage, which is just a Peltier element that we can cool down and record at what point each droplet froze. And you see this is then freezing, turning white until they all freeze. And we can, the temperature at which they freeze can be indicative of the activity of the particles that are in there. You notice here that this has been strapped down because a ship moves. Who knew? And therefore we had to strap every element of all of the whole lab down. And it was also interesting trying to pipette 1 microliter droplets on a cold stage when the ship is like going up and down on the sea. But it was great. It was fine. So yeah, so here's some of the data. This it's very preliminary, as you know, I've only just got back, but so this is just a fraction frozen curve. So on the y-axis we've got the fraction frozen, so it's the number of droplets frozen over the total number of droplets versus the temperature at which they froze. And you got all these gray ones here are the blanks, so it's just I think this is like handling blanks, so put plain water run through the system to just sort of to see what it's like without any ice nucleated particles in there. You can see that majority, and these different colors are my different impactor stages. So you see the majority of them are with it like kind of close to the background, which indicates that there's not a significant amount of activity there. But this orange here, which I did run a couple of times, with the same sample run a couple of times, we see that there's a distinct difference in terms of the temperature at which they froze, which indicates that we are seeing potentially some ice nucleating particles, and that is at stage A, which is my larger. So maybe it's large particles that are important. And this was, as I say, at this very first stop, which from looking at some preliminary looks at back trajectories, we're able to see that there was quite a lot of the air coming straight off of Greenland, so potentially terrestrial source there. Moving on round, so we stopped in this little fjord here, and this is a similar sort of picture going on here. Again, we've got the smaller size ranges kind of close to the background, and then maybe a little bit, not quite as distinct, but a little bit of more activity, like higher temperature freezing going on at that higher stage. And you know, for the sake of and then again looking at back trajectories on that, we were getting quite distinct flow coming off of Greenland itself. So again, maybe a terrestrial source. Then we went to the sea ice, And we were definitely distinctly getting, the flow was definitely coming off the ice itself, but all my samples are actually below my background, and that's, I suppose, most likely to do with the fact that I was directly collecting sea spray aerosol. So we get salt in there, so you get a freezing depression when there's salt in the sample, but also it just sort of indicates that there isn't maybe anything significantly freezing ice there, which is, you know, interesting in itself. So I decided to just quickly compare this to some previous data. So this is based on some work by C et al. In 2018. I think this is only based on sort of one sample collected in the Labrador Sea, but it's, you know, this shows the NS values, which is the number of active sites for nucleation normalized by the surface area with diameter. And you can see that there's like an increase in that ice nucleating activity. So they also saw these sort of higher rates of ice nucleation with larger particle sizes. So that seems consistent with what we're seeing, although obviously, as I say, this is still very preliminary, and I probably need to analyze my data a bit more, maybe actually calculate this NS value for my data and make those more direct comparisons. But at the moment, it's really consistent, and we've got some really interesting differences between the terrestrial versus the sort of more pristine air from the sea ice edge, which is really cool. Yeah, so overall, I've seen quite a lot of variation in my ice nucleation concentrations, but in general, maybe that those large particles might be more significant, which does correlate with some previous work. So it seems consistent and very nice. If anyone got any questions, I'm happy to take them now.
Thank you very much, Lindsay. Do you have any questions in the room to start with? Okay, sorry, I'm on.
Thanks.
I was wondering if there's any difference between ice aerosol and when you have the whole type, kind of that has to be accountable or something wrong.
Yeah, okay, in case that wasn't clear on Zoom, the question was, and not if it's right, the question was about like the difference between like how atmospherically relevant the cold plate is. Yeah, so that is a very interesting question, and it's actually really important, because even having the droplets in contact with something is not directly how it's going to be in the atmosphere, and they're actually quite a bit bigger than they would be in the atmosphere as well. Really, the technique that we use is more about statistics, so it's about how likely is that droplet to freeze at that temperature, and that's why we if I can, I try and run the same sample a couple of times, because it helps to like get those statistics more precise. But yeah, in an ideal world, if we wanted to be completely atmospherically relevant, that the cold stage just doesn't really do it, and definitely there are other potential ways, like, you know, maybe if we could get one of your EDBs like set up so that when we freeze and they still stay put, that would be really cool.
Okay, Dwayne Hurst from the University of Leeds. That was really fascinating. The aerosol that you collect from the ship, is that likely to be the same composition and size distribution as what is at higher altitude where the clouds are forming?
It's a really good question. And part of M phase will be to analyze this further. There is going to be a flight campaign in October, going out to Goose Bay, which is on the Canada side of the Labrador Sea, and doing flights. So like hopefully getting up to those higher altitudes and seeing if our measurements are comparable. But in general, by me doing my size distribution measurements, I can sort of see what sizes are these and how is that, and then do analyze it. We know roughly what kind of sizes are likely to get up to higher altitudes and be transported, because larger sizes fall out through sedimentation and much smaller sizes tend to grow. So if I can look and see, are these likely to be relevant to get up to those altitudes, and what kind of mechanisms might be there. But yeah, I think that's definitely something important to consider, and hopefully with the further campaign in October we can understand if they are comparable.
Thank you very much, Katie. In the interest of time, we'll have to move on, but thank you very much for your